Hello, my name is Kevin Chang, and my project is on how theta waves can propagate in a neural network without synaptic transmission at 0.1 meters per second. Theta wave is a strong oscillation wave that can mainly be observed in the cornu ammonis or CA area of the hippocampus. The CA area are all filled with densely packed pyramidal cells. Theta wave oscillation is a prominent 4 to 10 Hz rhythm in the hippocampal local field potential of all mammals studied to date. It is strongly correlated with behaviors such as memory and spatial navigation. Theta wave also plays a role in modulating the neurospiking of the hippocampal neuron, gating synaptic plasticity, and it is essential for the temporal coding of spatial information. Neurocommunication occurs mainly through synaptic transmission and gap junctions using neurotransmitters. However, neurospikes are observed in studies where synapses and/or gap junctions are blocked. The neuropropagation speed is still measured to be around 0.1 meters per second. One mechanism that can explain it is the electric field effects. Experiments have shown that extracellular fields can modulate the activity of single neuron and the network activity. In the hippocampal pyramidal cells, weak electrical fields can affect the excitability of pyramidal cells and the synchronization of the network. So the hypothesis of this project is that an electric field effect can underlie the propagation of neurospikes at a speed of 0.1 meters per second in the pyramidal neurons of the hippocampus. I'm trying to prove this hypothesis by using computational modeling. The model that I used for this project is a simplified model that was used in a similar study done by Chen Chu in 2015. I reference the article in the reference slide at the end of my presentation. The compartment model was built by using the program Neuron. I simulated a hippocampal pyramidal network because it is a typical region where theta wave oscillates. In the model, each pyramidal neuron contains 33 compartments, 1 compartment for the soma, 21 compartments for the apical dendrite, and 11 compartments for the basal dendrite. For the soma, the diameter is set at 10 micron with a capacitance set at 1 microfarad per centimeter. It also has a cytoplasmic resistivity at 155 ohms centimeter and a membrane resistivity at 680 ohms centimeter squared. For the apical dendrite, the diameter is set at 5.2 micron with a length of 735 micron. Its capacitance is set at 1 microfarad per centimeter and it has a cytoplasmic resistivity at 530 ohms centimeter and a membrane resistivity at 34,200 ohms centimeter squared. The basal dendrite has a diameter of 5.2 microns and a length of 790 micron. The capacitance is set at 1 microfarad per centimeter. It also has a cytoplasmic resistivity at 530 ohms centimeter and a membrane resistivity at 34,200 ohms centimeter squared. I also set the soma to have a active conductance and apical and basal dendrite to have passive properties. The model that I constructed on Neuron has 3 pyramidal cells that are not connected to each other. This allows me to study the neural propagation without any synaptic transmission. The figure on the left shows a top view of my model, and the figure on the right shows the 3D view of my model. As you can see in the figure on the left, the length of my model is 36 microns. This will give me about 3 microns between each of my model cells. A stacking factor of 30 is used. This stacking factor is estimated from the volume cellular density reported from histology study. In a mice hippocampus, a CA area, the cellular volume density varies from around 180,000 neurons per millimeter cubed to 300,000 neurons per millimeter cube. This is reference on my reference slide. Using a tissue thickness of around 600 micron, a stacking factor of 30 can be used to represent the cellular layout of the tissue. In my model, I injected two currents. One current is on the apical dendrite of cell number 1, as you can see in the figure shown in the yellow circle, and the other current is on the basal dendrite of cell number 1, which is also shown in a yellow circle. The electric field effects can only propagate the action potential in a transverse direction to simplify the model. That means that cell 1 can only affect cell 2, and cell 3 is affected by both cell 1 and cell 2 with electric field effect. The voltage at each node can be calculated according to the Ohm's law for conductors in the Maxwell's equation. The potential at point P at a distance r relative to reference electrode in the medium of conductivity sigma is shown on the equation on the left. Using superposition, this equation can be generalized to calculate the extracellular potential inserted at a target node N, shown in the equation on the right. After finding all the extracellular voltages at each node, I can divide those values by the membrane resistance to get every single input current in each node of cell number 2 and cell number 3. I can then use the eye clamp in the neuron program to inject the current in each node, and then I can look at the action potential of cell number 1, number 2, and number 3 in the voltage graph in neuron. The propagation speed is measured based on the intracellular recording of the 3 cells. It is calculated by taking the traveling distance and divided by the delay time. The traveling distance is 36 microns, which is the length of a model that contains my 3 model pyramidal cells. To find the delay time, I first exported the data of the voltage graph of my cell model 1, 2, and 3 from neuron. Basically, that's what you can see in the slide right now. And I imported those data into MATLAB. And from MATLAB, I can use a maximum function on the voltage vectors to locate the peak of the neurospiking of each of the 3 cells. After I found the peak, it will also give me the time of when it reaches the peak on the voltage graph. That's how I use to find the delay time, which is calculated by the difference between the time it took to reach the first neurospike in cell number 3 and the time it took cell number 1 to reach its first neurospike. I found out that the delay time is 0.248 milliseconds. Divide the traveling distance, which is 36 microns, by the delay time, which is 0.248 milliseconds, will give me the propagation speed, which is at 0.145 meters per second. So in conclusion, I hypothesized that electric field effects can allow theta wave to propagate between cells without synaptic transmission and at a velocity of 0.1 meters per second. This model demonstrates that pyramidal cell in the CA area of the hippocampus can propagate theta wave across each other at the same velocity as a synaptic transmission, which is also at around 0.1 meters per second. However, my model is not as detailed as it can be. I only used 3 cells, and I amplified it by using a stacking factor of 30. But in reality, the CA area in the hippocampus has way more pyramidal neurons in its neural network. This is most likely the reason why my calculated propagation velocity is not as close to 0.1 meters per second as I would like. This concludes my presentation. The following citations in this reference slide were used in the design, construction, and analysis of my experiment. Thank you.